Moniteers, and our customer is Professor Little, and our project is the Intellimonitor. Within our team is Chris Arensdorf, Matt Carey, Shawn Fitzpatrick, myself, Michael Tirgardoon, and Andrew Velasco. Now I'll hand it off to Matt Carey.
So, when our customer came to us, the project in question was to create a personal system for monitoring posture and movement. There are a lot of systems on the market today, and most of these are optimized for robotic measuring. We were wanting to look at human kinematics and have a system that's configurable for different human applications. So, we came up with a system of MEM sensors using 2 gyroscopes, an accelerometer, and a digital compass. Putting these together using Calvin filtering to get accurate angle readings to characterize posture and gait, we were able to create a system that communicated angular data and temperature data with the smartphone interface. So it allows the user of our sensors to actually see their movement on a smartphone that they carry while the movement happens. And we also communicate with a long-term database that stores information where a remote user or the same user later can go and see the same information over a long period of time. This website interface is secure, and we can see many applications that might arise from the system. See, maybe it could be used for athletic enhancement, maybe for monitoring the movements and activity of the elderly, or maybe even use in clinics where we could actually characterize the movement of different patients that are under question for different diseases or ailments or physical injury. So, when we visualized our system, this is what we came up with. We have the human here, the subject, who wears devices strategically placed in different parts of the body, depending on the activity in question, which will be set up on the smartphone interface. These devices collect data from his movement, from his posture, and send this data to the smartphone that he carries. I mean, everyone carries a cell phone these days, so it's not a big extension, obviously, the system from what you would normally carry. These devices that you wear are small, lightweight, and they do not impede your movement. And then the smartphone displays data for the user to see. Say he's looking at a specific activity, they're afraid he might bend his back to a bad degree. This will help him monitor his own movement. And then the data from the smartphone is transferred to our web server, where a remote user can use the website interface at intellimonitor.bu.edu to see the same data at most 10 minutes later after the activity is completed. This block diagram shows our system. It's a fairly linear system. Movement and temperature come in from the inputs, flow through our activity monitoring device, the AMD. The device transmits the data to the smartphone, and the smartphone to the web server. And at all points here, the user can see data out on the smartphone interface. There are also some LEDs that indicate status, and there's a vibration motor on the devices that the subject wears to notify them of the target activity that's programmed into the device. The deliverables for our system were a prototype of our activity monitoring device, as you can see in the top right. We've also provided a schematic and PCB layout files for the design for miniaturization of the device. We have a Windows Mobile 6 client application for your smartphone, web server with a database, and a web client interface at intellimonitor.bu.edu. And we've also provided documentation to help people use the system. Now we'd like to show a quick video that introduces what might be yet another application of our system.
This is Joe, and he works in a storeroom. Joe's boss is welcome because he's a really hard worker. However, lately, Joe's bosses have become concerned about his back because of Joe's bad lifting technique. So, Joe's bosses have decided to buy the Intellimonitor system to see exactly how Joe lifts. Here is Joe attaching an activity monitoring device to his thigh. And here is Joe attaching another device to his chest. With these 2 devices, you'll be able to characterize his lifting technique. Here's Joe's old lifting technique. The device on his chest vibrates, indicating a bad lift. Joe learns and revises his lifting technique. Here's Joe's bad lift seen on the smartphone interface. And here's Joe's good lift seen on the smartphone interface. Here is Joe's boss on the Intellimonitor website looking at data from when Joe was wearing the activity monitoring devices. And Joe's boss is happy to see that Joe is no longer endangering his back with bad lifts. Thank you, Intellimonitor system.
And now I'd like to pass the presentation off to Shawn, who's going to start to talk about our system features and hardware.
Okay, so I'll be talking about the system features. Our first feature, since we're using Bluetooth, we're allowed to use up to 7 AMDs, including, so 7 AMDs and then the smartphone will be 8. That's what a personal area network will allow. Also, the Bluetooth allows automatic connection, the establishment of a connection between the AMDs and the smartphone via Bluetooth. To the left, you'll see customizable configurations. This means that you're allowed to set where on the body you actually want these devices to be put. To the right, you'll see that we have a rechargeable lithium polymer battery, which we target to last up to 18 hours. This would mean that the user would be allowed to use it the length of a day and be able to recharge it overnight. To the bottom left, you'll see that our user interfaces have only 3 menu levels of depth. This includes the smartphone and the website. This makes it simple for the user to be able to maneuver around our applications. To the right, you'll see that we're collecting data in 2 planes. They're the sagittal plane and the transverse plane. We'll show a picture on the next slide of what they actually are. This is able to target specifically for a lifting application. You'll see pictures that resemble that. And on the bottom right, you'll see that we also have, as mentioned before, a secure website, which allows you to access data from the past, so you'll be able to go back and check what the user was doing previously. So this is a picture of our AMD prototype. On the left, you'll see that is the Bluetooth module right here. And we use the QE128 demo board, which is the HCSO8 microprocessor. And you can see all of our sensors here. And this is the thermistor, which is sticking up there. And now, again, like I mentioned, we use the 8-bit MC9SO8 QE128 for the microprocessor. The reason we use this was it had a bunch of different interfaces that we needed to use for the sensors. One was the A to C port, which we needed to use for the gyroscope, accelerometer, and the thermistor. It also has the I2C interface, which we needed to use for the digital compass, and the SCI UART, which was used for Bluetooth communication. We also use a timer peripheral for sampling rates. This means that the user will be able to they'll be able to set in the code where how fast they want this device to be taking samples, how fast they want to know what angles that the user is making. This also, we have software-based Kalman filters, which will filter the data to get the accurate angles. And also, we create the standardized packets with all these angles and temperature that will be sent through Bluetooth. So this is the pictures that I was describing. The top one is the sagittal plane, which we can see that you're able to measure angles in that plane, such as a trunk angle or a thigh angle. This is the M9A7260Q 3-axis accelerometer. This works in conjunction with the gyroscope, as Drew will talk about in a second, with Kalman filtering. The second one is the transverse plane, which uses the digital compass and a gyroscope. This basically sets, the digital compass will say where north points, and that's what we read the angles off of how much they've actually rotated. And Drew with Kalman filtering.
So in order to accurately measure and estimate body orientation in the transverse and sagittal planes, we need to implement a Kalman filter. These sensors alone can measure and estimate a angle of orientation, but they're not ideal. Each of these sensors has their own quirks. The digital compass measures and estimates heading based on its position relative to magnetic north. This digital compass can face interference from electromagnetic interference, and it's skewed measurement daily by passing through specific magnetic fields. It's also inaccurate when the unit is not level. So for each orientation being output, it's skewed by, worst case, 2 degrees per offset from a tilt orientation, to a tilt level orientation. The gyroscope measures angular velocity. It integrates this angular velocity over time to get a angle. Using a 4th order Röntgen calculation to numerically integrate this, it is accurate, but in a sense, the error calculated throughout each calculation gets combined and subsequently increased over time through this calculation. Since we want to measure absolute orientation as opposed to a change in orientation, a reference point would have to be obtained during each operation, and the estimated angle would have to be zeroed periodically to account for this truth. Due to that reason, the gyroscope alone would not be feasible or ideal. So the accelerometer can be used to directly measure orientation based on its position and